Hello everyone, very warm welcome once again to my YouTube channel Simulation Engineer. As you can see, today's topic is boundary layers with pressure gradient. I am doing this video because I came across really a lot of queries, a lot of questioning about boundary layers with pressure gradient, what it is, and everyone who has to deal with the fluid mechanics have heard about like favorable gradients, and zero gradient, what is uh, unfavorable gradient, or in other words, like what is an adverse pressure gradient. So it's not going to be a really very long presentation video. I will try to summarize it and to try to explain the concept of boundary layers with pressure gradient. So if we really go or start with boundary layers with pressure gradients, everyone, even if you are in your bachelor studies or doing masters, you're doing fluid mechanics, you have come across like flat plate analysis and equations for laminar and boundary layer flows. So normally whenever you are doing a flat plate flow analysis, this will really give you a good feeling how the laminar and the turbulent boundary layers really behave. But there is one aspect which is missing if you are dealing with this flat plate analysis, and that is the important effect, which is flow separation. Right? This happens in really a lot of practical applications. If it's an internal flow, either it's an external flow. And for the very first time, Ludwig Prandtl, in the early 90s, he showed that such a separation, it is caused by the excessive momentum loss that is near to the wall. And Prandtl has given this concept of boundary layer that near to the wall, you will lose a lot of momentum, and the flow becomes weaker, and it's much prone to the opposite direction of the mainstream flow. That is, in a boundary layer, the momentum loss will occur to move downstream against the increasing pressure, right? So meaning that your pressure gradient is like positive. So the pressure gradient will become much stronger compared to the velocity. Velocity decreases, pressure increases, and you have this positive pressure gradient, which is then called as an adverse pressure gradient. The opposite case of decreasing pressure, right? That is meaning that your pressure gradient will be then negative, meaning that it's a favorable pressure gradient and there will be no separation in this case. We will see just in a few seconds in the coming slides with examples how this really happens. If we really take into account a typical immersed body flow, the favorable gradient is normally it is on the front of the boundary, and the adverse gradient it takes place on the rear part of the boundaries, right? And this will be much clearer with this statement, which I actually mean is if you really see this figure, and this is the one which I was talking about earlier, that Prandtl had showed that the boundary layer separates, and how the separation occurs is because of this adverse pressure gradient. You see in both these cases, so the figure A, if you really see, it is kind of a mythical flow, so it's not really the reality that the flow is everywhere attached. You can see that it's even the boundary layer and wake is nicely attached, but the real flow, if you see the flow over a cylindrical body, or it's a blunt body, that's a Reynolds number of about 10 to the power 5. We see that here at this around this point the flow starts to separate, and there is a transition region, so goes from laminar to turbulent. In between there is this transition flow, and then the flow starts to separate. And the pressure, why this is happening is, if we really go back once again, that the favorable gradient is on the front and adverse gradient is in the rear part of your body. And what really happens that you have a very strong positive pressure gradient resulting in an adverse pressure gradient, and it dominates the flow by reducing the momentum near to the wall, and then all of a sudden you have an increase in pressure, and then the flow starts to retard, and it tries to go in the reverse direction. So just talk about in terms of some little bit theory, and which is the basic or the important equations. So if you now see that the flow separation, how you can define that, it can be defined with the geometrical argument, taking into account the second derivative of the velocity. at the wall. Yeah, so for example, if you have a flat plate, and we say if we take the second derivative velocity at the wall, and we know that from the momentum equation at the wall, where normally if we say that at wall we have a no slip boundary condition, meaning that your velocities are zero. As you go away from the velocity from the wall, the velocity starts to increase. Obviously there is a frictional effect, also the viscous effects, and then in that circumstances you obtain normally this form for both, either it's a laminar or it's a turbulent flow. This is really the equation. So if you really, this tau is the wall shear stress, and if it's you take the wall shear stress gradient that is at the wall in the y direction, this is the equation. You can write it in terms of viscosity and second derivative of your velocity, and we can write it that it is equal to the pressure gradient in x direction. So if we really relate these equations, we can reformulate, and finally you come up with this this formulation, and meaning that is that in an adverse gradient, in an adverse pressure gradient, your second derivative of the velocity, which is this one, yeah, meaning if you have your adverse pressure gradient, that this term dp over dx, right, this is a pressure gradient, this will be zero. It's an adverse pressure gradient, and that the velocity will be, it's like positive at the wall, yeah, yet it needs, or it must be negative at the outer layer. Outer layer means that y equals to delta. Delta is your boundary layer thickness, so y is like wall normal this direction. So there is a point at the velocity at where the boundary layer thickness is like about 99% of your velocity, free stream velocity at this point, which really merges or really somehow dissolves very smoothly within your mainstream flow, and that is your velocity, which is denoted here with capital U of x, that is in x direction. So what does this equation actually tells us? That it means that if the second derivative, that it must pass through your zero somewhere in between, that is at a point of inflection. So what is a point of inflection? I will be explaining to you in the next slide. And any boundary layer profile in an adverse pressure gradient. Yeah, and it actually must exhibit, or it will come out like a characteristics S shape. And we will see really in this general case, it's a standard flat plate flow analysis, a general case, and we have several behavior of the boundary layer, and these are all like subsequent flow behaviors. Like you start, let's say you have your body in somewhere here, you start at x equals to 0.1, you go to 0.5, 1 meter, x equals to 2 and 3, further downstream you keep on moving. So initially, this is one of the classical test cases or flow behavior. If you really see, like it's a favorable pressure gradient, as we have learned in the previous slides, meaning you have a strong velocity gradient going on in the x direction. You have negative pressure gradient. That means your point of inflection is really inside the wall. So as I mentioned previously in the last slide, so what is point of inflection? It is just a point. A point of inflection is just a point on your smooth curve at which, at that point, the curve changes the sign. So for example, if it is concave up, it might be concave down. So if it's convex, or it will be concave just across this point of inflection. That is simply this point of inflection. And we come back to our example. So we see that at this point, the point of inflection is not even visible. So it is inside the wall, no chance of flow separation, favorable pressure gradient. And if we talk about zero pressure gradient, our pressure gradient is like zero. And this is, once again, you see the velocity profile. Now the point of inflection is still on the wall, meaning no chance of flow separation. If we move further downwards, we will see that these three profiles will show the behavior of an adverse pressure gradient. Yeah, it has been marked here with dp over dx greater than 0. So we start with this C boundary layer profile. It's a weak adverse pressure gradient. Still, there is no separation. We have a pressure gradient, it's adverse, but the flow is like really prone to separation, but still the retardation does not take place. And the point of inflection is in the flow now. And if we move further downstream, we will see that there is this zero slope at the wall. You see this this curvature, it's almost right like perpendicular here to the wall. And at this point, your wall shear stress will be 0. Yeah, and this indicates that your separation will take place. Yeah, and if you go just a little bit further forward downstream, the momentum loss has already been taken place. It started at this point, and then because of having a very weak boundary layer, it does not have any strength to move in the same mainstream flow direction, which is this pointing towards the positive x. It starts to flow in the negative x direction, and there is an excessive amount of adverse pressure gradient, and you will have a backflow at your wall. And this is really the separated flow region. So this will really be your separated flow region, and this is the point where separation starts or takes place. Similarly, if we take into account a practical example, let's say if it's a duct flow, this is an internal flow. So you can divide it into three different portions. This is our nozzle. Yeah, that this is the throat of a nozzle, and then this is a diffuser, right? It like diffuses. So we have a nearly inviscid core flow, which is here, and near to the wall we have this, because of there is a boundary layer going on because of the viscous effects, and at the walls we have a no slip boundary condition, meaning that your u and y velocities are zero, as we assume that it's a two-dimensional flow in an xy plane. And if we see that at the nozzle we have a decreasing pressure in the area, the velocity all of a sudden increases, and there is a favorable pressure gradient, so there is no chance of separation. And then the flow comes at the throat area, where there is no change in the cross section, it's everywhere constant. So the velocity will remain constant, and the pressure is like, you have a constant velocity, meaning that there is a zero pressure gradient. And then the flow tries to follow the geometry, because now you will be getting this diffused effect. So it's kind of a diffuser effect. What will happen that if you go further downstream, it's the same principle as we have seen before, that it's in the flat plate, a general case, that initially it will be a weakly adverse pressure gradient, then it would start to become a little bit intermediate, and at this point you will see that now the pressure starts to dominate the flow, and the velocity is becoming a little bit less, because we can see from the velocity vectors, the magnitude of velocity is really quite strong here, and all of a sudden once you move here, you will see this change in the curvature. So this is the point of inflection, and this dashed line is showing your boundary layer thickness. So if you really see now the thick boundary layer becomes thicker, it's an indication that your pressure is now dominating the flow field, meaning that there is a decrease in your velocity, and then the adverse pressure gradient takes place. So we will be getting zero wall shear stress here. So this, at this point where wall shear stress is zero at the wall, your separation point takes place. You go further downwards, the flow is totally separated. It's a fully separated flow region, and the decrease in velocity, this is your flow reversal. So you can see the division of the streamlines at this point. Similarly, we can see the similar practical example in case of an external flow. It's the same as if you take into account like internal flow, you just turn it around upside down. So now we have an airfoil. We have a free stream pressure and free stream velocity coming in. If you see, and this is a stagnation point, and you can see now, you can easily see the difference. This is the upper part, so this is the suction side, and this is the lower part of the airfoil. This is the pressure side. Let's assume it's once again a 2D flow in an XY plane. And initially there is a laminar boundary layer going on. At this point we see that the velocity starts to increase, that is, flow is becoming accelerated as you go past the leading edge, and you have a strong curvature. It's a symmetrical airfoil, we assume that. And then the boundary layer region, this is everywhere, it's shown like a shaded effect. So if you go further downstream, you can still see that outside the boundary layer the flow is really inviscid, because the viscous effects are not even dominant. Yeah, the viscosity is really very important, and it's really dominating near to the wall. So if we see now, this is the transition regions. We have examined that this is almost here, this point, and then at this point is the laminar boundary layer, and then the flow starts to become turbulent. Yeah, and this can really be seen with this Fuller effect of a boundary layer, the much stronger gradient compared to the laminar flow. And then at some point there will be again this adverse pressure gradient. You will see here, this is the point of inflection, for example, and you go further downwards, you have really wall shear as zero at this point. the flow is now at this separation point, and then if we go further downstream, we have a very strong excessive adverse pressure gradient, and the flow is fully separated near to the wall. We see this flow reversal, and we can see this nice wake, symmetrical wake, which is really producing kind of a trailing edge flow separation on this airfoil. Okay, so I think with this I will conclude my today's presentation about boundary layers with pressure gradient. I hope I've been able to give you some information or the knowledge which really I have, and hopefully I was able to answer the questions you guys have been asking about the boundary layers with pressure gradient, and we have seen that what kind of different pressure gradients are available. If you have a favorable pressure gradient, you have a zero pressure gradient. Then there are several forms or several types of, let's say, adverse pressure gradient. You start with a weak one, go to the intermediate, and then there is an excessive pressure gradient flow. Yeah, with this I conclude my presentation, and I would encourage you guys to subscribe my channel, like the video, but don't forget to subscribe my channel if you haven't done it until now, and try to share my channel among your friends and family and community if you think that it's really interesting, and keep supporting me. With this, I wish you a very 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 nice day. Take care. Bye bye.